Okay, look at this example. Only show you how to use the psychometric chart. How to use the psychometric chart. For this case, use the psychometric chart to determine the absolute humidity. If you remember that the absolute humidity is in this axis, right? This axis is the absolute humidity. Wet bulb temperature. Wet bulb temperature. Sometimes this wet bulb temperature. The wet bulb temperature, if you know the condition, this point you drag the parallel line with the enthalpy across the saturation system. Saturation system is 100% relative humidity. And then you drag the vertical line, you get the wet bulb temperature. And also determine the humid volume. That's like humid volume. I will show you for the next. Okay. The next slide will show you the humid volume. Okay, this line for the volume, humid volume. Okay. And dew point. That's right. The dew point, it should be parallel line. So this is the dew point. Specific enthalpy. The condition is 41 Celsius and 10 relative humidity, 10% relative humidity. Okay, you need at least two conditions. If you know at least two conditions, you can calculate another condition, another parameter. That's right. And the last question, determine the amount of water in 150 cubic meter air at this condition. It is the diagram. Okay, I will show in detail for this. Okay. What is the condition? Condition is 41 Celsius. This is a 41 Celsius. Dry bulb temperature. Okay. And then you know the relative humidity is 10%. This is the 10% relative humidity. This is 20, 30, 40, 50, 60, 70, and finally 100% in this line. That's right. This is the condition. 41 and relative humidity 10%. We caught at this point. That's right. We caught at this point. At this point, you can determine or read the absolute humidity. Absolute humidity in this axis. Right. Okay. From this point, you can draw the vertical horizontal line to cross this point. Okay, you can read this approximate 0.004 as kilogram water per kilogram dry air. This is the absolute humidity. That's right. 1 kilogram of dry air includes 0.004 as kilogram water. That's right. In the air, we have some water in terms of vapor phase. Okay, from this point, you can calculate the dew point. That's right. You can calculate the dew point. For this case, you draw the horizontal line to cross the saturation line. This is the saturation line. That's right. Saturation line. Cross at this point, and then you draw the vertical line to cross the dry bulb temperature. You get dew point approximately 3 Celsius. That's right. Approximately 3 Celsius. And also, at the same condition like this point, you draw the line parallel to the enthalpy line. You can read the enthalpy of the set is 54.2 kilojoule per kilogram dry air. This is the enthalpy, that's right, for this point. And also in this point, you can draw at the saturation line from this point. Horizontal to the temperature, you get the wet bulb temperature is 90 Celsius. That's 90 Celsius. And also you can calculate the different enthalpy. This is the different enthalpy. That's right, different enthalpy. Okay, this point is located between these two. This is about 0.6, 0.8. It's between 0.6, 0.8. For this case, we estimate at minus 0.7 kilojoule per kilogram dry air. Right. Moreover, at this point, you can use this point to determine the humid volume. This line is the humid volume. It's 0.85, 0.9. The unit volume is cubic meter per kilogram dry air. This is the unit. Right. And this line we have 0.95. This line is 0.8. That's right. Okay, at this point, it's between 0.95 and 0.9. You can interpolate. That's right. You can interpolate. It's close to 0.9. It's between this point and this point. Okay, this point is close to 9. Okay, we can estimate at about 0.897 cubic meter per kilogram diameter. Okay, this is the example that I talked to you. If you know only the dry bulb temperature, that's like 41 Celsius and 10% relative humidity, you get only this point. You use this point to calculate absolute humidity, wet bulb, dry bulb, enthalpy, difference in enthalpy, humid volume. Okay, you can answer for our question. You can absolute humidity, wet bulb temperature, humid volume, dew point, specific enthalpy. Okay, the last question, you calculate amount of the water. That's right, amount of water for dry. Okay, the last question. Okay, this I show you already. Okay, the humid. That's right. For this case, you know the enthalpy is 54.2, and the delta S is -7, and finally you get the enthalpy is 53.5 kilogram per kilojoule per kilogram dry air. And the last one, that's right, the mole or mass of the humid air. Mass of the humid air. For this, the humid volume. That's right. Humid volume for the curve. Approximately 0.9897 cubic meter per kilogram dry air. And then we can use this data to calculate the mass because the volume, 150 cubic meter. That's right, 150 cubic meter from the humid volume. But that means 1 kilogram dry air includes 0.897 cubic meter. That's right, from this 1 kilogram dry air includes 0.897 cubic meter of air. Right? And also from the absolute humidity. Right? This is absolute humidity, 0.0048 kilogram water per kilogram dry air. But that means 1 kilogram dry air includes 0.0048 kilogram water. That's right. 1 kilogram dry air includes 0.0048 kilogram water. And then you can calculate kilogram of water. That's right. Kilogram dry air cancel. Cubic meter cancel. You get kilogram of water. This is the information from the psychrometric chart. You can use the psychrometric chart to calculate the water and air system. That's right. And also for the next example, we will use the psychrometric chart for the energy balance and material balance or mass balance. For this, we use the air conditioner or air cooler. That's right. We use to cool the temperature of the air. Okay, the air at 80% relative humidity and 80 Fahrenheit. That's right. Equal to 51 Fahrenheit. The cooling system. At the constant temperature of 180. Right. For this case, we will apply the psychrometric chart to calculate the fraction of water that condense. That might form from the vapor water. Some parts of the wet water condense to the liquid phase. That's right, condense to the liquid phase. And the rest at which heat must be removed to deliver 1,000 cubic feet per minute of humid air at the final condition. Okay, and then you can draw the drag that this the air cooler. That's right. We have the feed. For this case, we assume 1 pound of dry air in the feed. 1 pound of dry air in the feed. And the dry air. And we don't know the water. That's right. We represent by M1. M1 means the mass of water vapor in the air. That's right, water vapor in the air. For this case, we know the feed is 80% relative humidity. It's not dry air. That's right. It is the humid air feed to the cooler. But humid air includes dry air 1 pound mass and M1 pound mass for water vapor. And the condition, the feed is 80 Fahrenheit and relative humidity is 80%. You can use this to calculate S1, something like this. And the outlet, that's right, the outlet also air is the same, 1 pound mass dry air. but we have two stream of outlet. This is the humid air, includes air and water. We represent M2 is the power mass of water in terms of vapor in the air, and S2 is entropy of the outlet of the humid air. And the outer outlet is liquid water. That's why we have condensed water. M3 means the liquid water at 51 Fahrenheit. The outlet at the same condition. That's right. And also we have some heat. We represent by inlet heat because the energy balance, we balance based on inlet heat. But for this case, the real system, the heat should be outlet. That's why it should be removed from the cooler. Okay, you can get that after you calculate, after you solve, you can get the negative side of the heat. That's right, because it's opposite for this. We use the inlet because we balance. That's right, Q minus W equal to delta S plus delta EK plus delta EP. For this equation, we balance based on input heat. That's right, input heat. Okay, if you calculate and then you get the minus or negative side, what does it mean? It is the outlet heat. Don't worry for that. Okay. Okay, for now we have 1, 2, 3, 4, 5, 6, 7 unknown. That's right. M1, M2, M3, S1, S2, S3, and Q is unknown. We have one material balance. Independent, we have two, right? Water and air. But the water and air is all balanced already in the chart. Okay, we have only one independent balance. And we have the absolute humidity from psychrometric chart for inlet and outlet air. Okay, we know what it is. We know condition. That's right. We know condition. And also we know the enthalpy from psychrometric chart for inlet and outlet. That's right. Inlet for air. And we know the enthalpy of water. That's right, from the condition. And also we know one energy balance. Okay, we have the 0 degree of freedom. Okay, look at for the point 1. You know 80 Fahrenheit, you know SI is 80%. You can calculate S1. That's right. You can calculate S1. You can calculate SA like this. Right. For point 1, where is point 1 is we look at 80 Fahrenheit, 80% relative humidity. Okay, this is in the psychrometric chart. It's different unit. This is in terms of American or English, American engineering unit. It's different from previous example. Okay, this is 80 Fahrenheit, and this line is 80% relative. At this point, you can calculate absolute humidity 0.018 and enthalpy 38.8. Okay, this is the inlet humid air. And also you can calculate amount of water in the inlet air because you know the absolute humidity. That's right. You know this from SA. You know this from SA. Okay, one pound mass of dry air in the phase. That's right. But for this system, we know 1 pound mass of dry air input 0.018 from this data. You get this is M1. Okay, you can solve for it. The next step, you consider the point 2. Sorry. For M2, that's it. Okay, the next one for this. You know, right, 81 Fahrenheit, and also you know the outlet is saturated because we separate in the vapor phase and liquid phase. Okay, because it's saturated. Saturated. Saturated means the 100% relative humidity. You can consider like this point. Okay, this is 51 Fahrenheit. This is the saturated line at this point. Also, you can calculate the absolute humidity. You can calculate the enthalpy, right? Okay, from the second point, you know SA, you know S2. Also, you use this information to calculate M2. That's right, you calculate M2 at this point. From 1 pound mass of dry air. This is 1 pound mass of dry air. But from the psychrometric chart, you know 1 pound mass dry air equals 0.0079 pound water per 1 pound mass dry air. And finally, you calculate M2. That's right. Now you know M1, you know M2. Okay, the next step. For this case, we balance on water. That's right. For this system, we assume right, the inlet outlet flow rate is continuously. This is the steady state. And there is no chemical reaction. That's right. Water still water, only phase change. Air still air. Okay, no generation, no consumption. We get inlet equal to outlet. And then you balance allow the air cooler for water balance. That's right. To the water balance, the water inlet is M1 equal to outlet M2 plus M3. You know M1, you know M2. You can solve for M2 directly. Now you know M3. Okay. And the next step, you calculate the fraction of water condense. That's right, water condense. Water condense is M3. That's right, M3 is water condense. 0.01 pound mass of water condense. Divided by the phase water. Phase water is M1. Right. This is the phase water. It's about multiply 100, you get percent. That's right. Percent is about 55.5%. This is the amount of water condensed. That's why we feed 0.018. The condensed is 0.1. It's about 55%. Okay. And then you calculate the entropy of condensate. You know the entropy of inlet, outlet, but you calculate the entropy of condensate. For this case, you use a technique that you explain from the homework question 3. That's right, homework question 3. Okay, for this case, we shoot the temperature at 32 Fahrenheit at the reference state. And for this case, we can assume the CP is constant because the temperature is quite low different. If you compare to the Lika question, that's right, it's different, it's quite high. 100 to 500 is very, very high different. But for this case, okay, you can assume constant. Okay, for this case, you can assume constant, but the reality is quite dependent on temperature. That's right, on temperature. Okay, for this case, we reference to 32 Fahrenheit. That's right, the reference state for the water. Okay, the outlet water is 51 Fahrenheit. That's right, from reference to 32 Fahrenheit. Right, 32 Fahrenheit. For this case, only the integration term. We have only this. Only this. That means delta S equal to, sorry, delta S equal to S3 minus S reference. That's right, S reference equal to 0. That's right. That's equal to integrate CP dt like this from 32 to 51 Fahrenheit. That's right. You know the CP like this, it's CP. You convert from this unit to the American engineering unit. That's right, American engineering unit. This is the molecular weight of water. This is the temperature difference. That's right, because this is per delta T, not per temperature. That's right, this is the delta. That's right. And also this is the conversion of BTU per joule. And this is the conversion of gram and pound mass. You get this is 1 BTU per pound mass per delta Fahrenheit. That's right. Okay, and then you can substitute. This is constant. Okay, you can integrate dt, you get T. That's right. Then now you know S3 equal to 19 BTU per pound mass and water. And then you follow the energy balance. That's right. For energy balance, Q minus W equal to delta S plus delta EK plus delta EP. That's right. There is no moving part. That's right. The equipment is fixed. There is no moving part. No radiation, no electrical field. Okay, you can cancel the EK is 0. And also there is no difference between the location of inlet and outlet. That's right. The difference or the position quite small difference. Okay, we can cancel EP and no work. That's right. Okay, Q equal to delta S. And because the more than one stream, we use the summation outlet inlet. That's right. Okay. For this case, we have two humid air. We consider humid air, not air and water, because we can calculate the term of enthalpy in terms of humid air or dry air already. Okay. For this case, we consider humid air and water. Humid air inlet, humid air outlet, and water outlet, because the water inlet input in humid air already. For this case, you know M inlet, M outlet, you say for humid air. You know enthalpy already from the condition. Right? And also you calculate the enthalpy of water. Okay, now you know mass, you know enthalpy to this data for the case. And then you can calculate Q. Q is negative. That means correct, because the balance we balance based on inlet Q is positive. But for this case, the reality is outlet. You get minus mean the Q is outlet. Q is transformed from the system to surrounding. Okay, and also for this case, you can calculate the amount of Q, that's right, per meter of flow rate, heat rate. For heat rate, you can calculate based on the volumetric flow rate. You know the volumetric flow rate of the air. That's right, 1,000 cubic feet per minute. That's right, 1,000 cubic feet per minute. And also you know the humid volume. That's right, humid volume from the humid air as outlet. From this, you can from this of outlet, this is of outlet. That's right. It's approximately 13 for the humid volume. Okay, you know the humid volume. You multiply the mass of dry air, you get the volume of humid air, and then you multiply the Q with the volumetric flow rate and divided by the volume, you get the heat rate. That's right. This is the heat rate. Okay, before I move to the next slide, I would like to break for 5 minutes.